Okay. Just a few quick announcements before we get started with things like this. So Leo wanted me to remind everyone again that if you're expecting letters, packages that are that you should be checking that back corner, sort of when I'm looking at the clock to the left of it, and yeah, we're
just on that ledge right under.
Yeah, exactly. The physics office apparently brings those packages there. There's one there right now. Right. Anyway, and then a second announcement is that so today there's a slight modification to the schedule. So today, after the third lecture, which ends at 3:30, we're going to have Alex give continue his lecture from 3:45 for about an hour, just to get through a little bit more of the material that he was planning on getting through today. So this is not going to be on the website, or it's not going to be updated anywhere, but just spread the word if someone you know isn't actually in the room right now. I'm not going to make the announcement again, but at 3:45.
So. Maybe put it on the Slack channel.
Yeah, actually, that's right. If someone can upload that to the Slack channel, that would be helpful, since I don't have access to that. So, okay, so now, Liang.
All right, hi everyone. So let's continue our discussion about the Bosonic codes from yesterday. And maybe first I should point out that we're not, there's a long history of Bosonic codes, including like starting from the late 90s. And people are thinking about like how to do like optical quantum computing, and using some of the photon detector nonlinearity, you can actually also correcting some of the errors. So there was a big burst of codes in the late 90s. And also like about 10 years ago, there's another burst of the codes, because actually superconducting platform took off. And with the Josephson nonlinearity, we can actually do something such as measuring photon number parity. Okay, this slide is prepared by Victor, and he's a zookeeper for the old Bosonic code zoos, and now actually extended to all error correction zoos. So if you're interested in all error correcting codes, this is a website you should go to. Okay, and and also if you invent new codes, you should let Victor know. He'll put it on his website. Yeah. So now just as a recap, what we talked about the last time, we give one example of the minimum Bosonic error correcting code that uses a single mode to correct a single photon loss error. And the code is called the Kitten code. And basically, it's a superposition of 0 and 4 Fock states, and as a logical 0, and 2 photon Fock states. And we show that by checking the error correction matrix, it can correct both no error and single photon loss error. And one natural question is, can we correct more loss errors, or can we correct some of the additional like thermal noise associated with the heating of the system? So it turns out it's possible. If you look at the coefficients more carefully, corresponds to binomial coefficients. Sorry, there's no. And actually in here, you can actually generalize this to something called the binomial code. So the binomial code is specified by 2 parameters, capital N and capital S. So the S or S plus 1 correspond to the spacing between different code words. So here, if I do the even spacing, which plus 1 equal to 2, so that I S photon loss error according to the spacing. Okay, now the choice of the binomial coefficients ensures that the average photon number, or the higher order moments of the average of the photon number distributions, will be indistinguishable between logical 0 and logical 1, which means if you lose 1 photon or you lose multiple photons, from the environmental perspective, they're equal likely to happen. So as what Victor said, from an environmental perspective, there's no way you can extract the information about the encoded logical qubits. Then the logical qubits actually stay intact in the system. And then you can design error correcting codes to recover it. And here is actually the construction and for the binomial codes. And you can find it actually in the reference, which I put it on, which I just sent the link to Leo, and he can share it to you. Yeah. So now, furthermore, if you look at these codes, then there is also some symmetry properties on it. So let's look at, for example, on the screen here. And this is just the code. And if you look at upper right corner, this actually corresponds to a choice of the binomial code with actually S equal to 2 and N equal to 1. Yeah.
So S changes the number of photon losses you can
yes.
correct. What
So the N is something that makes sure that you have broad enough distribution of photon number. So for example, what's the maximum photon number for these codes? It's S plus 1 times N plus 1. That kind of gives you the kind of the largest N, that's the largest photon number you have. So if you want to make sure that the photon numbers, when you have the average photon number square, higher order moments of photon number being indistinguishable between logical 0, logical 1, you need to have a sufficiently large N so that its distribution is sufficiently like kind of a, how to say, you have enough parameters so that you can tolerate more of the loss errors. Okay, so there is some additional relation between N and S. The N need to be sufficiently large in order to ensure that all these errors can be corrected. And for that case, I would probably not write down all those relations, but it's actually, you can find it in this paper, PIX 6031006. So this is the work done in collaboration with Steve Gervin's group. And actually Victor gave the proof that, okay, why these high order moments are actually indistinguishable. Yeah. Yes, Leo. Yeah.
So S is fixed and not just the kind of error. It's determined by the kind of errors you want to correct.
That's true. So basically, suppose I say, oh, I want to correct up to S photon loss. Then you can fix S. Then you need to choose N to be sufficiently large, which some scale linearly with S. Then it will have a sufficient broad distribution so that you can make sure the higher order moments of the associated with the photon loss is also corrected. Why is that? Because you might remember there's this error correction condition, EI dagger EJ, sandwiched by kind of the projection of the code space. So EI dagger EJ, so pick an I to be A to the S power, and the EJ to be A to the S power. So that will be something equivalent to be like A dagger to the S power or A to the S power. And this is sort of like the highest weight of these kind of error patterns that you need to make sure you can correct. And this you can do the commutation relations of bosons. That's kind of also depends on all different moments of the average photon number or photon number squares up to the S moments. So you need to make sure that this is indistinguishable for logical 0, logical 1.
Meaning they have the same matrix element.
Meaning they have the same expectation value of A dagger A to K's power, K run from 0 up to S. Yeah. So that requires you need to have a kind of a binomial to be a little bit broader so that you can cover all these. These are just Fock states. Yeah, that's right. Yes, that's right. So just let's say N equal to 1, S equal to 1. So this guarantees you'll get only even photon numbers in there. And when P is even, multiply even number, it guarantees it will be multiple of 4, which gives you the kind of Killing code 4. Yeah, when P is odd, multiplied by S plus 1 is 2, that gives you the Fock states 2. Okay, yeah. Yes.
So for the hidden code, you mentioned that the actual single photon loss has an attenuation factor.
Yes.
Does this code follow?
Excellent question. Yes, you actually need to check that, and it's not obvious. So, the question is that for the Killing code, this is the sort of like idealized error models, but the realistic error models, which is actually e to the minus kappa t over 2 n hat, and then there is some combinatorial factors e to the minus kappa t n hat a, and with some like square root of gamma 1. So notice that these factors will redistribute the photon numbers because it will no longer be binomial because it will be multiplied by some exponential decay associated with the photon number. And then it will no longer guarantee that if you don't detect loss, the distribution will be slightly different from the original binomial distribution. So what you need to do is do some non-trivial local operation, this unitary, to kind of realign it with the binomial distribution. Okay, and it can be shown that the errors can be suppressed to high order. Yeah, and for the cat code, if you don't do error correction, the error is kappa t. But with the error correction, it's being suppressed to the order kappa t square. And here, if you can suppress all these, then it will suppress the error from kappa t to order kappa t to the power s plus 1. And that corresponds to suppressing like a multiple loss errors. Yes.
So the operators will be aligned by not the distribution is complicated there.
Well, it's a unitary, and I would say experimentally it's non-trivial. people did it for the killing code. Yeah. Okay. Yes. Oh, sorry. Here is a kappa t to the power s plus 1. Yeah. All right. So now, what I want to. Oh, okay. Yes. Yes.
I don't know much about like what are the other kind of errors you consider? What is the space of errors?
Yeah.
Like,
So, well, there could be errors associated with A daggers, and there could be errors associated with A dagger A, which one corresponds to heating, the other corresponds to dephasing. Okay, and actually, like here, I don't want to like get too much into the discussion here because there is actually a phase diagram you can look into with a different choice of N and S in terms of the loss and the dephasing you can tolerate. And for example, here, with a sufficient large N, you can also trade off between how many loss errors you can correct versus how many heating errors you can tolerate. So for example, maybe you can say I correct from identity A to and then A to the S minus 1. Then I can add another error which is associated with A dagger. So that I may, since the separation between the photon number spacing is S plus 1, you could consider lose up to certain number of S minus K error, and you can consider heating associated with K errors. As long as those two don't overlap, then there's sort of a guarantee or differentiate between loss and heating errors. And then you need to check the error correction condition that indeed there is no information, or at least this condition is proportional to the projection. So there's no information leakage. Then you can claim it's a full error correction code up to certain loss and certain dephasing error. Yeah. So, but I would say like the other point is that notice that for the hidden code, this is like the spacing is S plus 1. And here we can easily see that it's always even. What does it mean by it has an even photon number? It means it's an eigenstate of this operator, which we call the parity operator, right? Because when I apply parity operator, this gives eigenvalue plus 1. And what does the parity operator mean? You can write it as e to the I pi times n. That means it's a 180-degree rotation in your phase space. So therefore, you can actually have this 180-degree rotation symmetry. Now, if you look at the binomial code, this is actually has a symmetry, which is no longer pi. It will be 2 pi over S plus 1 times n. That means if your n kind of like so if you kind of like rotate the phase by the angle, which is 2 pi over S plus 1, this will actually give you, it's an eigenstate of this operator with eigenvalue plus 1. That corresponds to you rotate the phase angle by 2 pi over S plus 1. So now suppose actually that in the upper right corner of that plot, maybe I should make it bigger, that actually corresponds to the choice of S equal to 2. So S plus 1 is actually 3. So 2 pi over S plus 1, that corresponds to like this 180-degree rotation. Then you will see that this code actually has this the threefold symmetry for that particular choice. And here you see the sixfold. I think it's because actually we choose a particular code word that being shown. Yeah. Yes. Yeah. Okay. So yeah, maybe. So here KT means that you let the system evolve for a small time t with a photon loss rate kappa. And this was kind of like defined in the master equation we explained in the last lecture. So this is the probability for each excitation to be lost. And if you don't do error correction, this will be the error probability. Now with this hidden code, we can show that all the errors are suppressed to the KT square, which means if you have say like a KT equal to 10%, initially it's 10% error. With error correction and the recovery, you can suppress the error to be 1%. Okay. Okay, so how the powers of KT? So here, maybe because I can correct these errors, And let's tentatively ignore these back action, the factors. That corresponds to the correct no loss, single loss, roughly. Then what's left behind is 2 photon loss. 2 loss, that's a KT square. Now there's some subtlety that I mentioned last time. There's some back action, and you need to make sure you do some additional unitary to suppress those back actions, also to KT square. And altogether, it's consistently, everything gets suppressed to KT square. Yeah, okay. Yeah. Yes. 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 So here, when you say, I want to compute a function of a dagger A to some case power for this code word, it will give you a function of capital N, capital P, and also mu. Mu corresponds to logical 0, logical 1. Okay. And generally, it will have mu dependence. But the claim is if N is large enough, sorry, and then S, and you will no longer have the mu dependence when this K is small enough. Okay. Yeah. And then you can show you fulfill the question condition. This is the exact statement. Yeah, I don't remember the exact condition. If I roughly it's N larger than S, but okay, then I might be missing some prefactor here. So N increase linearly with them when enough higher order photon loss. All right, so now let's actually move on to the other code word, which is the cat code. And actually, cat code was proposed like even earlier, but here is actually a reference which gives more explicitly, like actually the 4-legged cat that can correct like a photon loss errors. So let me first write down the code word for cat code. And here, I want to make a similar analogy because I go from kitten to cat. So I want to kind of make the basis to be aligned as well. So I would choose it to be alpha plus I alpha plus minus alpha plus minus I alpha. So if you think in terms of phase space, I have 2 special points as alpha, I alpha, minus alpha, and minus I alpha. So these are the 4 different coherent states. And I try to write it as a superposition of these coherent states. But since just want to confirm that how many people know like what is a coherent state? If you know, please raise your hand. Okay, great. Yeah, so the coherent state is basically a superposition of different photon numbers with a coefficient as the square root of the Poisson distribution. Okay, yeah. So this is a logical state. And if you think, take the limit, alpha goes to 0. Okay, here with some like, I should put the proportionality factor. Sorry, too many alpha. So this is a normalization factor that I put in to make them to be normalized. And you can see that this will approach 0 Fock states if alpha is 0. Okay, but when this is for alpha approach 0, but generally it will be summation of photon numbers which are multiples of 4. Okay. Okay, sorry. Yeah. Thanks. So maybe I'll write this way. So this will be a summation of photon number for n. So what are the coefficients? So just remember the coherent state alpha consists of alpha to the k's power divided by square root k factorial with a photon number k with a normalization coefficient. You don't need to worry about it. So then when you add those up, when you have I alpha, when you have minus and minus I, when you raise to certain powers, then you'll have a cancellation of these coefficients unless the power k is equal to integer multiple of 4. Because when you take integer multiple of 4, I to the 4th power or minus 1 to the 4th power and the minus I to the 4th power, they're all equal to 1. So they add up coherently. And that is why this logical 0 state will be equal to superpositions of these coefficients. Okay. And now notice that this another way to see it is this is a symmetric superposition of these states, which means if I rotate 90 degrees, they will be the same state, right? Because it's an equal superposition. And if I rotate these 90 degrees, just some permutation of the alphas, and they'll get to the same state. And the 90-degree rotation corresponds to some like e to the I pi over 2 times the photon number. And the way to make this to be equal to 1, it implies n need to be integer multiple of 4. So that 2 pi, pi over 2 times 4 equal to 2 pi. So this would imply this n hat should be integer multiple of some constant k. Okay, so that is why we need to have photon number to be integer multiple of 4. It's because this is a 4-fold rotation symmetry. Okay, now we can define the similarly logical 1 state. So with some normalization, and this time I will do it in such a way, it's alternating plus and minus sign. Once I do alternating plus and minus signs, then you can still plug in these photon numbers with alpha to different powers. You'll find that for photon number 4n, it will actually cancel because this will plus, this will minus, plus, and minus. Only for photon number, which is 4n plus 2, then it will not cancel. And that actually maps back to the Kitten code. When n equal to 0, this is the 2-photon Fock states. And notice that the difference is that over there, the coefficients I choose to be binomial coefficients, while here the coefficient Cn, it actually corresponds to the Poisson distribution. Okay, yes. Alpha can be a real number. Let's say alpha is a real number larger than 0. Can be a continuous choice of alpha. Yeah. All right. So now, the good thing is we restore something similar to the Kitten code, which the photon number is evenly spaced, so that if you lose a photon, at least you will detect it by parity. Okay. However, the cat code actually have some like approximation in there, because there's no guarantee the logical 0 and the logical 1 have exactly the same average photon number. And there is also no guarantee the higher order moments of a photon number are exactly the same. Okay, so basically you can compute what's the average photon number for logical 0 and logical 1. And they are approximately equal, but the separation, or let's say what's the difference, it will scale as e to the minus alpha square. Yes.
I'm sorry for asking you. Can you explain like what this alpha actually represents?
Okay, good. So it is a continuous number. And when I say it's a coherent state, I say it's a coherent state with amplitude alpha. And I can define the state alpha as a superposition of where the coefficients is of powers of alpha to the Fock state k. Okay, this is a mathematical definition. What is the physical definition? So you might recall I talked about this mass and spring, right? And the alpha corresponds to the maximum displacement A0 divided by this x0 point fluctuation. So that gives you a dimensionless number, which basically tells you about the maximum amplitude of the oscillation that such an oscillator may have. Okay, and another way to think about, we know that amplitude square corresponds to the energy, right? So the alpha square actually corresponds to the average photon number in the system. Okay, that's the definition for also, you can compute it from this definition of coherent states. All right, yeah. So if you say a coherent state with amplitude alpha, that literally corresponds to the amplitude of the oscillator in units of the 0 point fluctuation. And alpha square, also dimensionless number, corresponds to the number of excitation, the average excitation in the system. So what you can show is that these averages are typically very close to n bar. which is alpha square. But there is a little bit deviation because when alpha is very small, then this actually are not exactly equal. But when alpha is large enough, the average photon number is the same, almost the same for logical 0, logical 1. And this is actually related to what Victor was also talking about like yesterday. It's approximated error correcting code that approximately satisfy the Canary-Lam condition. Okay, and notice there are different levels of approximation. Here, so first approximation is say over there, we may have multiple photon loss and we just ignore it. And that's approximation. And here is say, even if we don't have multiple photon loss with just a single photon loss, there are already some approximations in terms of satisfying the error correction condition. But it's a really good approximation because it decreases exponentially with alpha square. So typically when alpha is say like equal to alpha square equal to 2, there's also some small prefactors there. So typically when we choose like average photon number n equal to 2, we already can suppress the error to be this approximation is good enough, better than 90% or 95%, so on. And if you choose alpha equal to 4 and more, then basically that error can be negligible for any practical cases. Okay, yeah. So now one thing is this code is actually has some classical analogy. You might recall I talked about the phase shifted keying, which is to encode information in the phase of a coherent state. And here, if I were to do this with a classical coding with these 4 coherent states, I can encode 2 classical bits based on the phase is 0, 90 degree, 180 degree, or 270 degree. However, in this quantum case, I'm not encoding 2 quantum bits, I'm only encoding 1 quantum bit. It's because I need this additional redundancy to only use the even photon subspace rather than the full 4-dimensional subspace. I choose only the even subspace so that I'll be able to detect every single photon loss. And that's the additional requirement you need for quantum coding. And that's the reason actually we have a smaller logical space compared to what we would do for the classical phase shifted key. And that's where the connectivity is from between the quantum codes and the classical code. Yes. If I want to worry about quantum, I can encode the 2 bits in here. That's right. Yeah, because I could, it's a 4-dimensional subspace. Yeah. So now, one thing which will actually be related to the later discussion is that one might ask, how can we actually prepare such a state, right? Because it's more complicated than even the CAT, which already been non-trivial to prepare. And here is actually like one condition that actually will be interesting to point out. So maybe just a remark. So this can be stabilized by the following operator: a to the 4th power minus alpha to the 4th power. Okay, since this is we're talking about the Lindbladian open quantum system, suppose you have a quantum jump operator like this, then it acting on any of the logical states will be 0. Why is that? You can check that if I use the coherent state alpha, plug in here, a to the 4th power will bring out alpha to the 4th power, which cancel with this term. And I can say I do a plus or minus alpha. Doesn't matter whether I put a plus or minus sign, raised to the 4th power, it will be canceled. And if I do plus or minus I alpha, when I raise to the 4th power, it doesn't matter what's the coefficient I put in there, because raised to the 4th power will bring equal to 1. So that will give a cancellation. So therefore, any states for these ones or their superpositions will be annihilated by this operator. Okay, so this is actually an interesting jump operator, and you can show it has a 4-fold degeneracy in the steady state subspace. So this gives you 4-fold degeneracy. And now notice besides the fourfold degeneracy, this operator always preserves the photon number modulo 4. Okay, because you either take away 4 photons or you don't do anything. So what happened is that now if you start from vacuum, you can just turn on this operator, turn on this jump process with the Lindbladian kind of master equation. Then it will prepare this logical 0 state. You just need to wait for it to approach this steady state. And because of fourfold degeneracy, it guarantees it will only go to one out of those kind of in those 4-dimensional subspace spanned by these alphas and the plus minus I alphas. But there's only one state which has a photon number that's equal to integer multiple of 4. So if we start from vacuum, it will give you that state. If we start from a 2-photon Fock states, it will give you this state under this engineer dissipation. Yeah, okay.
Sorry, could you guarantee that you get to this?
Yes, it actually will guarantee. So the argument is the following. So first, with this engineer dissipation, I know it's a 4-fold general subspace spanned by these 4 states. And these 4 states, I can write 4 different linear combinations. Here I listed 2, which has a photon number 4n of photon number 4n plus 2. I can also have another combination with the photon number 4n plus 1 and the photon number 4n plus 3. But there's only one state which is all the photon numbers are integer multiple of 4. So if I start from vacuum, it will guarantee to end up in that particular state. Okay, so that's one way to prepare such a non-trivial state. And of course, you may ask, it's a non-Gaussian state. Where does the non-Gaussianity come from? It comes from this engineer dissipation. This is not quadratic, okay? And it's actually a bit non-trivial to engineer such a term. However, the people are actually working on this as well. And you can generically design a scheme to construct such an engineer dissipation. Let's call this to be jump operator J. So we can design a Hamiltonian system, which is J times, let's say, have another lossy mode B plus J dagger B. So this is a Hermitian operator as a Hamiltonian, which needs some high order nonlinearity, but suppose we have this, and then combined with some dissipation process, let's call it J prime, that's equal to the single photon loss rate in mode B. Combine this Hamiltonian with this dissipation, and if the dissipation is much larger than Hamiltonian strength, then what happens is you can get an effective dissipation, which is equal to J. That's the one that you want, and then you can put the J something like this, and by constructing a Hamiltonian and a very lossy cavity mode, you can obtain such an effective dissipation. Okay, so this is a bit more like, in theory, you can do it this way. And experimentally, I think they can construct such nonlinearities. The practical challenge is if you want to have some high order nonlinearity, you need to make sure those lower order nonlinearities are not causing an effect to your system. So you need to cancel those lower order nonlinearity in order to maintain, to let this high order nonlinearity to be significant. Okay, yeah. So now we can further generalize a bit more. So comment number 1, stabilization. Second comment is that this code actually, with such a stabilization, it has high error bias. So now in this notation, let me just draw the block sphere. So the north pole corresponds to logical 0, and the south pole corresponds to logical 1, which here you can think a superposition of 4 n's, and this is a superposition of 4n plus 2. And this is actually in the photon number basis. And maybe it will be good also to think about the plus state, which is a symmetric superposition of logical 0 and logical 1. And if you look at those two terms, you'll find that actually when alpha is large enough, n0 and n1, they are approximately equal to a precision which is only deviated by e to the minus alpha squared. So let's say alpha is large enough, the normalization coefficients are almost the same. Then when you add the logical 0 and the logical 1, you actually get to the plus logical state, which is essentially alpha plus minus alpha. And the logical minus state is I alpha plus minus I alpha. So this is a block sphere. And if you think in terms of the phase space, so the logical 0, this is the logical plus, and the other ones, which I don't like fill it, that actually correspond to the logical minus. And when alpha is large enough, these logical minus and the logical plus, they are well separated in phase space. So if you have some small errors, it's actually unlikely to mix between logical plus and logical minus. Okay, it may leak out, may induce a relative phase between logical plus and minus, but it's very difficult for it to mix between the two. So that means that if you think in terms of block sphere, all the errors will happen to be some random rotations around the plus and minus this axis, but it's unlikely it will exchange between plus and minus. So this will be the dominant error for such a cat code, while it's exponentially suppressed to have some other errors that mix between plus. So you can imagine if I in the ideal case, if I can really design a code and realize it, and then the dominant error I will have is actually like a random rotation around the x-axis of this block sphere. Then what I can do next is at the next level, I just do a repetition code. Okay, so that it will suppress this remaining error. And if everything can be done fault tolerantly, then basically I can achieve an effective error correction with sort of concatenated correction. So at the lower level, I do the cat code to suppress such an error, and the next level, I can only do the repetition code to suppress the remaining error. And this is actually some key features associated with this error. So in this case, with this notation, the epsilon x, so the x errors will actually turns out to be proportional to the photon number. It's okay, it depends on how you design it. Maybe let me say this way. The z error or the y error will be exponentially suppressed. So that will give you exponential protection. While the epsilon x, it will be suppressed by higher level coding. And notice here, epsilon x for this cat code is not too bad because we are able to correct a single photon loss. And when you have a single photon loss, you can correct it. But when you have two photon loss, you cannot correct, which induce this x error. So it will be kind of kappa alpha square t square. And that it may still be finite compared to that exponential suppression in the other axis. So this will be suppressed by higher level like coding. All right. So yes.
Again, so why you get plus and minus
Yeah.
Very large.
Yes. So the definition of plus and minus is just the symmetric and anti-symmetric combination between logical 0, logical 1. Okay, and if you look at those terms, so I have the logical 0 being 1, 2, 3, 4, and the logical 1 is the plus minus plus minus. The minus term will cancel and only get the plus term, which is alpha plus minus alpha. Okay, and when you take the difference, it's the I alpha plus minus I alpha that shows up. So if you think in terms of the phase space, what you get is this is a logical 0, and that's a logical 1. So logical 0 is along the real axis, and logical 1 is along the imaginary axis. And if the alpha is big enough, then the separation is kind of like a square root of 2 alpha. So that's where like you need to make like a diffusion of these blobs by this amount in order to be mixed with the other blobs. Yeah. First, we need a superposition between alpha and minus alpha. The reason is that will ensure we are in the even photon subspace. And similar here. But now one potential error is that suppose you have dephasing. and somehow you rotate by 90 degrees, then the logical zero, a logical plus will become logical minus. And this is the error which would be really bad. But fortunately, for this coding and this such a stabilization, if you have some like small dephasing error, what had happened is that for such a stabilization with these as a steady state, what you can think is that there are 4 fixed points in the phase space, which associate with alpha, I alpha, minus alpha, and minus I alpha. And any deviation from that, you'll be pushed towards that fixed point. So when you have some dephasing errors, it will actually be pushed back to those steady state points or subspace. Then therefore, it will be exponentially hard to move from here over there.
So if I was just doing just the regular logical 0 and logical 1, I would actually get very.
And that's right. Yeah, but it's important. You need to put this engineer dissipation there, because if you don't put it there, it can do anything, right? Yeah, so that's actually like one advantage, that if your system, you can put some continuous engineer dissipation, it will help you to continuously suppress errors. Yeah. Yes. Good point. Yes, we do have the stabilizer actually stabilized to a larger subspace than the logical space. So that's why we actually still need to do additional error correction, which is measure the parity. Okay, and actually that leads to maybe the next thing. How do we measure parity non-destructively, which was a question that we kind of leave at the end of the last lecture. Yeah. So, but before I move on, first, are there any questions about the stabilization in here? Yes.
People routinely do super condensation. This is much higher voltage. How viable?
Yes. So, well, I would say like in principle, it's possible to design it, but in practice, it is not trivial. And I would say actually we proposed this about like 10 years ago, and people are still working on it. However, the good news is that actually the property, this high error bias, you can achieve it, this exponential bias, but maybe here instead of the square, you just do it linear, then you only need 2-leg cat. So if you're being kind of like less kind of like demanding, let's just say encode the state with alpha and minus alpha. And all I need to do is suppress the dephasing error exponentially because alphas are large enough, they're separated. Then I can maintain this exponential suppression that mixing between alpha and minus alpha. Okay. And at the same time, because it's a cat code, we know the cat states are pretty fragile. When you lose the excitations, the fringes will be destroyed. So here is actually like you rely on the next level of repetition code to suppress this like photon loss associated with the cavity. Okay, so here the 4-leg cat, the 4-leg is because there are 4 coherent states, we say 4-leg cat. It can correct a single photon loss. Well, if I do the 2-leg cat, I cannot correct a single photon loss, but I rely on the next level of error correction to correct a single photon loss. But experimentally, this is much easier because maybe you can already guess from the pattern of what is the engineer dissipation we need to suppress a 2-leg cat. And this is a jump operator that we will need, which will stabilize the subspace spanned by alpha and minus alpha. And this is easier because it's a quadratic. And when I plug a quadratic J in here, then I basically need a cubic Hamiltonian, which is more feasible in practice. And actually, people are doing such an experiment. And this is kind of the efforts at the kind of at Yale, they kind of pioneered this effort. And then they're actually like companies like Alice and Bob and Amazon AWS. That's what the people are working on to stabilize such a 2-leg cat. Yeah, Leo, yeah. 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 Yes. Yes. So one way to think about potentially you can break the symmetry is actually if you lose photon to the environment and not doing the error correction. Okay, not doing the parity measurement. So what happened is that suppose let's have a two-lead cat for simplicity. So let's a two-lead cat go through a beam splitter. Goes through a beam splitter. So there's some photon loss to the environment. So we know that for coherent states, if you have a coherent state goes to a beam splitter, the environment also gets a little bit like small coherent states that to the environment. So if you have a two-lead cat, the environment may be getting a small like a coherent states depending on whether the cat is on a state alpha or it's minus alpha. And then the environment probably can do a homodynamic measurement to know whether it is the left leg or the right leg. And that tells the environment which leg it's in, and that effectively erases the fringe between the superposition of these two coherent states. So it is true, it becomes very vulnerable. And or you can say like, if we don't do any active error correction measuring photon number parity and correct it, then essentially it will be collapsed to one of those coherent states. Or mathematically, you can model it as you have another jump operator, which is a single photon loss. And once you put in these together, the solution is no longer a twofold degenerate subspace. It will be a one steady state, which is an equal mixture of alpha and minus alpha. Yeah, so that's where the symmetry breaking happens. But if we don't have that, then there is a parity symmetry, which turns out to lead to a two-dimensional logical space.
It's like here channel.
Yeah. That's right. Exactly. And maybe to this like a Majorana fermion chain, we make that additional symmetry that there is a fermion parity is preserved, right? And if you allow to have a quasi-particle tunneling, then you actually will break that symmetry. So practically similar, maybe in that scenario, you might also require some additional higher level coding to correct that symmetry. Yeah. Well, yeah, well, in the ideal world, it's exact, but when you have environmental quasi-particles, then that would also contaminate that. Yeah. Yes.
So can you explain why it's quadratic, like error in X?
Oh yeah. So here I jumped multiple steps. Okay. I skipped a few steps. So suppose what's the epsilon x? It corresponds to I go from this state to that state, which means it's a two-photon loss event. And to have a two-photon loss event, this is the probability of a single photon loss. Then I squared, it's kind of a second-order effect of two-photon loss. Yeah. Yeah. Yes.
But it seems that the two-legged cat is just like a classical thing. Is that a
Yes, yes, exactly. It's a classical switch, right? We have its left or right, okay? But the non-trivial part is we want to maintain a superposition of left and right. Yeah, which makes it harder. Yeah, yeah. Which we do know, like a classical switch can stay in one of the states very, very long time, right? But here, the difficult engineering part is that you need to make sure it's a good superposition. Good enough so that you can apply error correction so that it can be maintained. Yeah. So now let's actually talk about the physical implementation. How do we measure the parity, which is crucial for both hidden code and also the cat code. So I will jump to the So here, the challenge is how to measure parity non-destructively. Non-destructively. And the idea is actually to use a two-level system to do a Ramsey measurement of the photon number parity. So starting point is the following. So you can imagine, let's say this is our cavity, which has a photon in there. And we have a two-level system. And that's a superconducting qubit. Let's say it's transmit with a Josephson nonlinearity. So the Hamiltonian will consist of this oscillator for the cavity, and plus the two-level system where the excited level is E, and the ground excited. And this is our two-level system with omega Q. And when the two-level system and the oscillator, this is omega cavity, when their frequencies are sufficiently different, you do not change the excitation between two-level and the oscillator. But there is a second order process that you actually virtually can have a two-level system, the excitation goes here and hop back. And this hopping back and forth process, when you hop it to here, there is a bosonic enhancement factor of square root of n. When you hop it back, you'll get another bosonic enhancement square root of n. So this virtual hopping back and forth process will actually give you a bosonic enhancement, or will give you some high A dagger A, if it's excited state or if it's ground state. So you can think alternatively this as like a kind of a cross-Kerr coupling between the two-level system and an oscillator. Okay, so now this quantity typically can be of order megahertz, which is like an inverse of a microsecond. And these cavities can be of order gigahertz. And what's important is this megahertz, the dispersive coupling, can be much larger than kappa or gamma, which kappa corresponds to cavity loss and gamma corresponds to the two-level relaxation, which is of order like kilohertz or tens of kilohertz. So you can induce this effective unitary evolution without suffer too much of the relaxation of the cavity or the two-level system. So this is, say, kappa, and this is gamma. And we know our superconducting qubits can have a coherence of like 100 microseconds, and our cavity can have a coherence better, like milliseconds or longer. Yeah. So now you don't need to worry about the numbers. Basically, the key point is this is a good approximation to model this as a unitary evolution under this Hamiltonian. Okay, and actually you can go to the rotating frame, just ignore those terms for the oscillator and the cavity. So what's left behind is this dispersive coupling. So this dispersive coupling you can interpret in two ways. One is the excited level of this, the level of this excited state. There will be an energy shift. Depends on how many excitations are there in the cavity. Or effectively, you can think that the cavity level spacing gets modified depending on whether the two-level system is in the ground state or excited state. It's kind of like a quick switch modified the frequency. So here we can take the perspective as the two-level systems, the excited level gets actually a frequency shift by amount high times the number of excitations in the cavity. Okay, so now we can imagine to have such an evolution, which is the unitary e to the minus I, this h times pi over chi. So here I assume I'm already in the rotating frame, so I ignore those intrinsic oscillations or rotations of this oscillator and the two-level system. So now when I evolve under this particular magic time, pi over chi, so what happened is, if I take the perspective as there is a frequency shift of the excited level, but I evolve for time pi over chi, this chi cancels that chi. So that means e to the minus I, A dagger A, E. So pi A dagger A, you can interpret as every photon will introduce a pi phase shift for the excited level of this two-level system. Now, if I have a dagger A, which is n number of photons to be even, then it will be pi times the even number, which is 2 pi. So e to the power 2 pi is identity. So it doesn't matter whether it's excited or ground level. This will be just the same. It's just basically like a trivial evolution for our two-level system. So now if the photon number is odd, then what happens is you will accumulate a pi phase for the excited level, because this overall factor is odd integer multiple of pi. So this will become e to the minus I pi EE. Or equivalently, you can write it as GG minus E. Okay, so this is the evolution, because notice at the end, it only depends on photon number parity being even or odd. Then the two-level system evolve under identity evolution or under 180-degree rotation around the z-axis. All right, so now here is the procedure to measure parity. Step number 1, prepare the two-level system as a symmetric combination of ground and excited states. That's also the procedure that people do for Ramsey experiment or for like atomic clocks. You just prepare the atom in a superposition and then let it process over time equal to pi over chi, which is exactly that evolution. So now the last step is to measure whether the system is in the equal superposition or asymmetric or antisymmetric superposition of ground or excited states. The reason is because this evolution combined with the initial state, it will map it to, if the photon number is even, it's identity. So this will be the ground plus excited. And if photon number is odd, that's the evolution. So there will be extra phase applied to the excited states. So it will become ground minus the excited states. And notice that these two states are completely orthogonal to each other. So you can design a projective measurement to unambiguously tell between the symmetric and antisymmetric states. And that will give you exactly one classical bit of information about the parity, which is what we want. That's the key point. We only do projective measurement over the two-level system, and the answer still stays there. Get classical information about the property of the oscillator, which is parity, and nothing more.
Where's the information in the cavity?
Yes. So the states, originally you can have some superposition of photon number states in here. But after this measurement, suppose the measurement is even, measurement is a symmetric states, they have even number of photons, then basically you will only need to pull out those even coefficients. I think that's the superposition, and that's the remaining state of the cavity. And notice that we never do any measurement on the state there. Depending on the measurement outcome, you pick up the even coefficients or the odd coefficients. And the remaining ones, it basically is just a, how to say, it's a branching like with a either even subspace or odd subspace.
But your logical qubit, if your logical qubit is not odd and even, is it?
Yeah, exactly. The key point is when we choose this kitten code or four-legged cat, the logical qubit is something called a super parity, right?
Even or
It's a 4n or 4n plus 2. And when we measure this quantity, we actually measure the parity, which is to make sure whether we are in the logical space or in the non-logical space. And that parity measurement does not differentiate between logical 0 and logical 1. Okay, a question? So suppose it's odd, then as we talk about the binomial code, this would imply the state this gets to the 3 photon state, and this gets to the 1 state, and you need to apply the unitary to map it back to the original code word. But notice when you measure its art, you don't collapse the superposition between 3 and 1. So the information is still there, it's just in a different subspace. But that's okay because we can do unitary to restore to the logical subspace. Yeah, question? Yeah. Yeah, so this is actually the Hamiltonian, which has been studied in the superconducting circuits. And I think in 2009, actually in Rob Shilkoff's group, they actually built such a device and measure spectroscopy. And they prepare this in the coherent states and they measure spectroscopy of this 2-level system, and they see the Poisson distribution. The reason is the coherent states here correspond to a Poisson distribution of photon number, which correspond to a Poisson distribution of energy level shifts for the excited states. And then they studied further and verified that the magic part is about the superconducting system. You can get good nonlinearity and with very little decoherence in terms of photon loss in the count. And in principle, AMO systems could approach this, but I think people are still working on this. Yes.
Can you explain again why you're able to ignore transitions between states that are induced by the constant? Between say G and E. You go to like second order side.
Oh, yeah. So you mean how we get this Hamiltonian? Is that?
And that term is fine. Why
Okay.
don't you get terms that say excite the ground? If I start transforming the ground state, why don't you get terms that excite it to the excited state?
Oh, yeah. Suppose the excitation is here, but the transmon is in the ground state.
Yeah.
The reason that this is mismatched is that the kappa omega c minus omega q is much larger than the exchange rate for the excitation between the modes.
That's what he already integrated out and got.
Yeah. So if you look at that further, the chi is something like a second order perturbation. It's a g square over delta omega. Okay, but to do the full calculation, you actually need a third level of transmon to do it correct, to make the sign to be correct. Yeah, but that's probably a bit more detail on that particular platform. But the point is, there is a way to induce such a dispersive coupling. And the coupling strength is much larger than the coherence, so you can let it evolve and do this Ramsey experiment to measure the photon number. Yeah. Mm-hmm.
Can you do the if I understand correctly, Google restores their qubit
In here.
here. Can you do the converse for use the photons to measure?
Yes.
Make sure you
To-
see if you've left the code space of the.
Yes, and actually that typically what people do is they make a very lossy cavity and they let the photons coming in to measure the transmon. Because the transmon shifts the frequency of a photon when you when you measure it, you will see a different phase shift of the reflected signal. That's right. Yeah, and you can design it so that you can probably even differentiate between GE and F and so on.
But you probably don't want to differentiate E and G. That's your qubit.
Yeah.
You want that.
Yes, and actually, like there are some more recent developments. Like actually, that's a proposal from Amazon, and maybe you can ask Alex for more on that. You can prepare like 2 transmons there, and prepare in some logical state to be the GE plus or minus EG. And then if there's any relaxation, you can measure it from the cavity, assuming these have the same dispersive for the frequency of the cavity. And that gives you some like a non-demolishing measurement of detecting the leakage error while still preserving the information that's stored in these in the double transmon design. Yeah. So now actually for this platform, let's say it's still a good cavity and like ancillar transmon. This is actually a very powerful platform because experimentally, what people can do is they can measure the transmon, say with another cavity, and they can, based on the measurement, they can feed back to the cavity. Okay, so it's a platform which you can see. This is a platform. It is a platform. I have, say, cavity, and I have a transmon. Now the information is stored in the cavity. The transmon is ancillar, and the ancillar transmon has the capability to be refreshed, be measured, and also conditioned on the measurement of the ancillar transmount, we can do feed forward to do additional operation on the transmount or cavity. Okay, so with this capability, I can design any quantum process for the cavity. Okay, so here, so far I was just saying I do a parity measurement of the state in the cavity, which is one of the CPTP process that the quantum process allowed by quantum mechanics. But my claim is, with this capability of this dispersive coupling, you can do arbitrary quantum process for the cavity. And the design is actually the following adaptive circuits. So generally, like if you look at the standard textbooks, suppose a cavity I want to say D levels. And the standard textbooks will say I have a D level system. And what I need is a D square level ancillar. And I apply a unitary and throw away the ancillar. And I can obtain any quantum process acting on this D level system. Notice if D is 10, you need a 100 level ancillar to do this and throw away the ancillar and to do this quantum process. Very resource consuming because you actually require more ancillar than your system to do it. So, however, it turns out that if you can do adaptive control, which is kind of also related to the theme of this workshop, it's now like you only need a 2-level ancillar. It can already help you to do something non-trivial over the D-level system. The trick is you need to repeat and do this adaptive control. So the procedure is basically the following. So you initialize your ancillar, let it evolve under a unitary U0 with this cavity, and you measure your ancillar, could be G or E, and then you reset your ancillar to be G, evolve under another unitary U1, the step 1. But the choice of the U1 depends on the classical controlled by the first. And one way to show it is that you can draw a binary tree. So suppose initially you have a U0, and the condition on the measurement outcome, this is a G or E, you will do either U1 G or U1 E. Then you will have another adaptive measurement, GE, and then condition on measurement outcome. Now this time you have 2 classical bits of measurement outcomes to control the third unitary U2. And this time the U2 will have 4 different choices. U2GG or U2GE, U2EG, and the U2EE. By doing this binary tree, you actually can quickly grow the number of possible branches, which is related to the cross rank of a CPTP map. And how deep we need to go through the tree, the depth of the tree is upper bounded by log 2 of the cross rank. Now we know that typically for D-level system, the maximum cross rank you have is D squared. So this will be upper bounded by 2 times log 2D, which is, if you want to go like 10-level system, you probably only need to do like 6 steps. Then you can already have a universal control over a 2-level, over a 10-level system. And notice that the example we talk about with the parity measurement is just doing 1 stage. We measure parity. But you can actually do more. And moreover, this actually gives you an arbitrary CPTP map, which is the most general process that allowed by quantum mechanics. And with this process, it includes initialization, measurements, thermal noise, and error correction, because quantum error correction is a CPTP map. Okay, so in principle, I could say with this capability of this general statement, any bosonic error correcting code, if I have perfect ancillar, perfect unitary, perfect measurement, okay, for all these other things are perfect, I can do any quantum error correction. Okay. Yes. Oh, the cross rank. Okay, so yeah, let me just write it more explicitly. So generally, we know that we have a quantum process is rho goes to epsilon rho. That gives you another density matrix. And epsilon rho, sometimes we write it as a cross operator kj rho, kj dagger. And j go from, say, 1 to some number. And we know there's a sort of a gauge degree of freedom of choosing the kj. So you sort of optimize that choice. So you minimize that the number of kjs that you need. And it turns out the number of kjs you need is always no larger than d squared. So this is n is the cross rank. N is no larger than d squared, where d is the dimension of the system that you have. Yeah. Yes. Yes. Okay, excellent question. Yeah, so far I assume that everything here is perfect, right? But in practice, it's not. And also one of the motivation of storing information in the cavity is because it's a bit longer lived. Besides, it has more levels for error correction. But in practice, like these transmounts are noisy, and they can decay. And they can decay during these gates, and maybe even give wrong measurement outcomes. And that would actually induce error. Because any such error, even though it's epsilon, but I do multiple steps, and ultimately, the error, the performance of the code I will get will have this additional term associated with errors associated with the transmount in this process. And that's actually something in error correction language is called, this is not fault tolerant. Because you're using a noisy device to measure an encoded system, and the noise in your device will actually be passed through your encoding blocks. So this is actually one of the challenges. However, the good news is we can design operations so that the errors in the transmount do not propagate back to the system. And there are some of the design principles that can be helped to achieve such a task. So one of the examples is actually, which I mentioned here, like we measure parity within a two-level system of a transmount. Now, if there is a decay of this transmount during the evolution, then you can imagine the cavity initially has a certain frequency, omega cavity, and the omega cavity shifted by the excited state. Then at some time, the cavity gets shifted its intrinsic frequency. So they actually will not be fully restored to the original coherent states that it should be. That will induce an error. Now, one solution to solve that problem, since we still have it here, let me just, is actually to design this the coupling. Now, instead of using the ground and the excited state of the transmount to store information, you actually use the ground and the second excited state to store information. So now the modification is, instead of say I start from G plus E, I start from G plus F. And the Hamiltonian will have an equal dispersive shift between the cavity and the transmount for excited state E and the second excited state F. It's important that the chi-E and the chi-F, they are the same. So why that helps? Okay, let me explain. Now, previously, the concern was when it relaxed from excited to the ground state, it can relax at any time during this parity or this Ramsey measurement. And this randomness of the any time it can relax will cause effectively a dephasing of the cavity. And it's a non-trivial big dephasing. Okay. Now, what if we say we do the G and F encoding? If it relaxes, F will go to E. But we know the Hamiltonian has shift for chi E and chi F, which means doesn't matter when F decay to E, the cavity will have the equal amount of frequency shift. Okay, so you can think that this Hamiltonian, the system is evolving under this Hamiltonian, starting from say F or E, and it may decay from F to E at some later point. But this decay process actually commutes with this Hamiltonian. Therefore, it doesn't matter when the decay happens. It can happen somewhere in the middle. This is equivalent to the decay happen at the end. Okay, so this is what we call the error transparent condition. So that this transmon relaxation error commutes with this underlying Hamiltonian, at least commutes for the particular subspace we're interested in. Then therefore, happen in the middle, it's equivalent to say error happen at the end. Okay, and if such error happen at the end, we will be able to detect it because it end up in the excited states. And what we do is we can restart the process because the whole system undergoing a fixed determined unitary, we can just cancel that unitary and repeat, and no information leakage or erased by the process. Okay, and moreover, if you think in terms of the quantum field theory, there is a version you can generalize to master equation that you can think there are different these decay trajectories. There are different kind of path integral associated with the Lindbladian Liouville equation. And all those different paths, they will end up in the same points. And those different paths are equivalent up to a unitary. Then that corresponds to the path independent condition. So the keywords for this will be error transparency, which was kind of introduced by Elliott Coppett. And then later we can generalize to something even more general called the path independent. And that allows you to sort of achieve a fault tolerance to suppress the dominant errors associated with decay. Yeah, but I would say this is still like active research investigations because we need to come up with a full set of gates to do it. Yeah. Yes. Yes, so and actually that's a question we also thought about as well. And it would be nice if we can do the CAT code and also continuously measure parity, right? And make sure it's stored in the even parity subspace. And however, if you look at the parity operator is actually a very, even though it's easy to write down, but it is actually a non-trivial operator if you expand it in terms of creation annihilation operator. So the parity is -1 to the n. When you do Taylor expansion, it's an infinite series. And if you think our Hamiltonian consists about like different powers of creation annihilation operators, you may have like a really high order powers from the n. And that's actually very difficult to implement with our limited nonlinearity we have in practice. So, but that's not the end of the story. There's actually a way to get around it. And the way to get around it is actually to do something of a different type of codes, which I also like mentioned it in the briefly in the notes. That's actually called the pair cat code. So the cat code uses a single mode to do encoding. If you do pair cat code, then what I can do is I need to specify two things. One is what's the stabilizer. And here, inspired by the a to the 4th power, I have two modes. So I have a squared, b squared minus gamma to the 4th. Second, I need to specify something similar to parity. That corresponds to the photon number difference, which defined to be NA minus NB. So this is another type of code. What it does is that it reduces the typical task to do this such a highly nonlinear term with single mode to something with 2 modes. Of course, here the power is still equally high, but the difference is that the parity now becomes the photon number difference. So just to give some intuition about what the code was, so you can get a logical 0 to be sum over n's with a 2n, 2n for cavity A, cavity B with a coefficient Cn. And the logical 1 corresponds to sum over n dn with photon number 2n plus 1, 2n plus 1 for A and B. So notice that here, the information is encoded still in the even and odd parity of photons. The way to check whether or not I lose a photon is check the photon number difference between A and B. Now, there are 3 different possibilities. One is no photon loss. The photon number is equal for A and B. Second is there's 1 photon loss in A, then I measure this. I could get 0, +1, or -1, which associate with the B photon loss, no loss, or A photon loss. And by doing this way, I can continuously monitoring the photon number difference, which is a lower power, and then to do also stabilize the logical space. And this is actually also a proposal that actually like Victor Albert came up with. You can ask him for more, which is called the pair cat code. And there are also designs of how to implement these in a both continuous fashion so that we can do autonomous error correction, not only stabilize to a space, but also correcting errors. Okay, but the key challenge is you need to make sure that the operator you measure is something feasible in practice. Yeah. Yes. Okay, yeah. All right, so I think I talked most about the code and for the cat and the binomial. And let me actually maybe introduce the GKP code. And maybe the next time we can talk more about that. Yeah, so let's do it this way. So in order to talk about the GKP code, one of the, I need to give you a preparation, which is actually we're talking about the loss error right now. And but the GKP code was actually originally designed to correct added thermal noise. But here is actually equivalence, say, not equivalence to say like kind of I can reduce or convert the loss error into something as added thermal noise. So for example, if I start from a coherent state alpha, with attenuation, it will become a smaller coherent state. Still pure coherent state, but a smaller amplitude. But one way I can restore to the original amplitude of the coherent state is to do some amplification. And by doing the amplification, actually I will amplify not only the signal, but also the noise. Okay, and the more detail is, in order to achieve amplification, one way to do it is you put in another oscillator, which is in a vacuum state, and do 2-mode squeezing. And that will amplify both this original oscillator and also make it slightly entangled with this additional ancillar oscillator. And if you trace out the ancillar oscillator, what you get is a thermal state, a displaced thermal state with a bit more uncertainty. It's because when you amplify the amplitude of coherence, you also amplify the original vacuum noise. So that's where you get this conversion between the loss error to be the thermal noise. So now if you can have some error correcting code can correct this added thermal noise, then that code can also correct loss error. The reason is if before I use the decoder, I first apply this amplification, convert the loss error into thermal noise, and my error correcting codes can correct the thermal noise. And that's actually where we're not able to actually use some other error correcting codes that was originally designed to correct thermal noise to correct loss error. And that code is called the GKP code. Okay, so, but before I introduce that, it may be first to look at the classical analog of a GKP code is something called the quadrature amplitude modulation. So this time, different from a phase shifted keying, I store information in both position and momentum, or in terms of amplitude and phase, I can store information in both amplitude and phase. So in order for this to work, I need to know what's the loss fraction. Okay, what's the loss rate for the individual, for this channel? so that I can amplify it to restore the original lattice. Now, the classical case, I don't have any like this like a quantum noise, right? I can amplify it without introducing noise, ideally. And that's why actually this code could help you to encode a lot of information. So for example, here I use 14 or 16 coherent states, I can encode 4 classical bits of information. Now, the quantum analog is I try to design some superposition of these coherent states so that the superposition will allow us to correct loss error, which is again introduce some redundancy to have a smaller logical space to correct error. Now, here, with the goal of this GKP code originally designed to correct added thermal noise. So one feature we know about quantum mechanics is it cannot measure both position and momentum arbitrarily precisely simultaneously, right? Because of the Heisenberg uncertainty principle. If we could, we can just know which lattice it's in and then just like adjust that error. But in practice, it's actually, we cannot do simultaneous measurement of position and momentum. And that's what the Heisenberg limit is. But however, you can get around that by performing some other operations. So here is a kind of inspirational way of writing the logical states, but actually a good way to write the GKP states is actually using something called the stabilizer formalism. Okay, so you write a set of commuting operators so that the state is a co-eigenstate of a set of commuting operators. So here, I'm just showing zoom in of the previous lattice. And let's look at the blue arrows first. So those are associated with something we call the stabilizers. So the xz corresponds to a displacement along the momentum direction by 2 times square root of pi. Okay, I'll be clear why we need the square root of pi for a moment. And the displaced sx corresponds to displacement along the position direction by 2 times square root of pi. Now, notice that sz and sx, they actually commute with each other. The reason is use the property of e to the I a times x, e to the I b times p, e to the minus I a times x, e to the minus I b times p. Okay, and this is actually proportional to e to the I phi, where phi is a times b. Okay, and this is, it's because that these operators, even though they don't commute, the commutator between x and p is actually a constant. So that basically there is some curvature in there, and once you loop around it, it's kind of the phase accumulated is proportional to the area of the loop that you enclose. Now here, we're actually choosing a equal to b equal to 2 times the square root of pi. So therefore, phi is equal to 4 pi, which is the integer multiple of 2 pi. Therefore, this phase is actually integer multiple of 2 pi, so this is equal to identity. Now you can move these two terms to the other side. Then what it tells you is e to the I ax times e to the I bp equal to e to the I bp times e to the I ax. So these two operators, they commute with each other. And that sets the stage that I can call these two things as stabilizers, which they commute, and I can define co-eigenstates for stabilizers. Okay, and now think about it. These quantities, they're not Hermitian operators, right? You might worry how we measure them. It's okay, you measure it multiple times, okay? You can measure the real part, the Hermitian operator, you can measure the imaginary part, that's fine. And also, by measuring these operators, what you get is actually something non-trivial. The sz tells you about the position modulo pi, modulo square root of pi, because that's what this phase tells you. And the sx tells you about the momentum modulo square root of pi. That's what this operator tells you. So we cannot measure position and momentum precisely, but we can measure position modulo root pi and momentum modulo root pi to arbitrary precision, because those operators kind of defined in such a stabilizers, they actually commute with each other. Okay, so this is a kind of a way to evade the Heisenberg uncertainty principle by being kind of less ambitious in terms of the information you get, because you only get the position momentum modulo some constant. And that allows us to say if you have a small displacement in position momentum, smaller than the lattice spacing, then you can actually identify those displacements and restore to the original lattice. And that's the idea of the GKP code by measuring these stabilizers SD and SX. Okay, so that's how it actually corrects the errors. But now maybe let's start in the next lecture how we actually encode the information in the GKP code. Basically, you take a square root of a stabilizers, you can get these logical operators, and you can show they satisfy these sets of commutation relations. Most importantly, X and Z anti-commute, that indicating it's a qubit. Which, if you're familiar with the toric code, that's sort of the way to define those logical X and logical Z as the loop operators. They actually anti-commute with each other. That indicating there's a logical qubit encoded in the system. Okay, so maybe we'll continue in the next lecture about the GKP code. Okay. Yeah. Yes.
So can you just say again what's the sort of analog here to classical code?
Yeah. So, yes. Good. So here you see these are blobs, and turns out that there's a way to write the GKP coeigen states of SZ and SX as a superposition of coherent states, and separated by actually square root of pi. Yeah. And you can find such a superposition, which is okay, slightly more demanding because this can be arbitrary spacing, but here you need to be a square root of pi. Yeah. Yes.
Well, I didn't understand the classical.
Yes. So classical part is basically I have these, for example, like an alphabet of like 16 coherent states. I send one of the 16 coherent states, then I would imply as setting 4 classical bits. If I send this coherent states, indicating it's a 1, 1, 1, 1. So that means that with a single wave packet of one out of the 16 coherent states, I send you 4 classical bits of information. And the 4 comes from the log to 16. Yeah. So this is a lookup. So when I send you a coherent state, you measure it. You measure both position and momentum. And if you find it's in this state, you say, oh, the bits that I received is 1110.
There's no arrow correction of something.
Well, actually, in some sense, it's classically, you can assume you can get amplification with no noise. So if you send the signal, it gets smaller, it's getting closer, but you can amplify it because classically you allow arbitrary amplification with no noise. And then you can know like what the original lattice is. But in order for this scheme to work, you need to know the amount of attenuation of your channel, which classically you can calibrate it by sending kind of laser beams back and forth, or maybe send some like a calibrated signal to measure it. Yeah. Yeah.
How isn't your phase space continuous? Are you associating the 16 blocks?
Yes. So here it's a convention need to establish between the sender and the receiver. Yeah. So you set a convention and then you do it. So there's a trade-off, right? You want to communicate with minimum power. On the other hand, you also do not want to kind of get confused with different states. And I think classically, you might imagine that these things, this coherent states we send in the qubit domain have thermal noise. It's actually quite a lot of thermal noise in there, like hundreds of thermal excitations there. So you need to make sure during that attenuation with these thermal noise blobs, they don't overlap in the presence of attenuation. Yeah. This is purely classical. But in some sense, it does have some similarity if you. Yeah.
So here again, information just encoded in position.
Yeah, position and momentum. But the key is here you measure position momentum arbitrarily precise continuously, while here we don't. But the trick to get around is to introduce these stabilizer operators with a careful choosing spacing so that you can measure the position momentum modulo square root of pi precisely, so that we're not violating the uncertainty principle. Yes. Yes.
But in this case, you can get away by measuring one.
Yeah, measuring two stabilizers. And the subtlety is these two are non-Hermitian operators with real imaginary part, and the eigenvalues are continuous real numbers. Okay, so that's a lot of information you extract.
One integer.
Yes, for cat code, we actually just measure one integer, the parity. And the reason is actually the error model is simpler. You don't need to say which qubit has error. You only need to know whether or not there's excitation loss for cat code.
And is this physically?
Well, it depends on the error model, whether it's a good representation of a reality. And for superconducting cavities, at least the dominant errors are photon loss, and there's some dephasing. But for cat code, when you apply this engineer dissipation, that suppresses the dephasing, and the loss error you just correct it by parity. Yeah. Yeah. So you need to know some models about your physical system, then design the code to correct those. And that's the reason why the Bosonic codes may look much simpler, because you only need to measure smaller sets of operators to detect the errors. Yeah. Thanks. Yeah, Leo.
So I'm trying to sense, so like this whole array that contains just one qubit.
That's right. At least for this design. Yeah.
Maybe on the chip you would have many.
Yeah. So this array is a single cavity, which is the phase space of a single cavity. So if you want to encode more qubits, you probably will have more cavities to it. Or for communication, you probably will send more wave packets. Each wave packet, the phase space is characterized by this array.
So my unitaries then would have two cavities at a time.
Yes, if you want to do 2 qubit gates. And then actually I talk more next lecture. The good thing about the GKP code is the 2 qubit gates are very easy. You can do it with a quadratic Hamiltonian, which is some like beam splitters or tumor squeezer. And that give you some 2 qubit gates like a CNOT gate, which usually typically needs. Yeah. Yeah. But I'll talk more about the how to use the GKP and how to do universal computing with the GKP, because so far actually it's all the Clifford gates are relatively easy for GKP. But if you want to do some like magic state injection, it turns out you can get vacuum from magic state by projecting to the GKP space. Yeah, just a teaser for tomorrow's lecture. Yeah. Yeah.
Stabilized by making the lattice compound projected that want to position.
That's right. Well, okay. So here, this is a complex number. It's a general operator, can be give you complex eigenvalues. Yeah. And now if you are really in the GKP state, in the lattice, then moving this SZ corresponds to move from here to there. And if you originally it's a perfect lattice, we displace that with the translation symmetry, it will give you to the original states. So if the GKP logical space corresponds to code SZ and SX equal to 1.
Right, so that's your code space.
That's a code space. Yeah. But if we measure it not to be 1, say it's 0.9 plus 0.1i, then that would imply that you need to do some display. It's shifted by some direction, both kind of position and momentum. Yeah. Yeah. So that's actually like the way to extract information to know like what's the displacement. But it also has a limitation, because if we displace more than this spacing, then if we under thermal noise, it goes more like it goes 3 lattice sites, then it will make an error, because it will say, no, it's probably going to some other lattice sites. Yeah. Yeah. Okay. Yeah, thanks.